Happy birthday, class. We'll be talking about the birthday problem. Here's the setup. This is a great problem. Suppose that there are n people in a room, like our classroom. Let's find the probability that at least two of them have the same birthday. We'll ignore February 29th because, as I said before, that's for freaks, and we'll assume that all 365 days have equal probability. That's not actually true because birth patterns vary over the year, but for simplicity's sake, we'll assume that it is true for now. So the simple sample space is S of all n tuples such that each element in the n tuple is between 1 and 365. So those correspond to the days of the year of each of the n people in the room. So x1 is the first person's birthday, x2 is the second, ... xn is the nth person's birthday. So note that this sample space has cardinality 365 to the nth power. This is a big sample space. So I'm going to let the event A be the event that all birthdays are different. So we're going to want 1 minus the probability of A. Anyway, the cardinality of A is, since there are n people in the room, this amounts to choosing n birthdays out of the 365. So this is the permutation of 365 things taken n at a time. And the way that we get that, well, we pick our first birthday, 365. Pick our second, it's got to be different, 364. Pick our third, got to still be different, 363. And it goes all the way down to 365 minus n. Remember, we have that nasty plus 1. But that's what the permutation of 365 things is taken n at a time. So here's the probability of A. Probability of A is that permutation of 365 taken n at a time, that's the numerator, divided by the cardinality of the sample space, 365 to the nth power. All I'm going to do now is I'm going to just break up the terms one at a time. So the first 365 is divided by one of the ones from the denominator, and that gives me a 1. Then I get 364 out of 365. Then I get 363 over 365. ... Last term in the numerator is 365 minus n plus 1 over 365. Okay, so that's the probability that everybody has different birthdays. Therefore, we want the complement of that event, probability that there's a match someplace, is 1 minus the probability of the previous mess. That's all it is. And we can calculate this out just on a calculator or Excel for different values of n. So note, when n equals 366, it's easy to show that the probability of A bar, the probability that there's at least one match, is 1. For the probability of A bar to be greater than 50%, it turns out that n must be at least 23, which is very, very surprising to me. So what you do, you plug in n equals 23, and that probability will be a little bit over a half. Very surprising to me because I would have thought you needed more people in the room. But it turns out 23 people allows for lots of potential matches, and it works out that indeed the probability is greater than a half. It also turns out that when n equals 50, the probability of A bar is way up there at 0.97. So if I've got 50 people in the room, the experiment never fails. Or at least I cheat. So anyway, this is a wonderful problem, lots of generalizations. And there are papers out there on this topic. I leave it to you to take a look sometime. So in the next lesson, we'll be doing another application of these cool counting techniques. So we'll see you in a little while.